Welcome to the module on challenges and opportunities in material repurposing. This section focuses on the challenges and opportunities in battery material repurposing as a key enabler of a circular materials economy. Demand for batteries is rising across mobility, electronics, grid storage, and industrial systems, so the volume of end-of-life batteries is increasing rapidly. Many of these batteries still contain meaningful remaining functional value and recoverable material content, making repurposing a strategic step before final recycling. Repurposing extends the useful life of materials and components, capturing more value from the energy, labor, and critical minerals already embedded in manufacturing. It also helps reduce near-term pressure on virgin raw material extraction and lowers environmental impacts linked to mining and refining. Economically, repurposing preserves asset value by enabling secondary uses, generating revenue, and improving total cost of ownership, supporting a circular battery economy that is both more sustainable and more resilient. Material repurposing generally follows two broad pathways, depending on the target market and the level of processing required. The first pathway is closed-loop repurposing, where recovered constituents are refined and re-engineered back into feedstocks suitable for producing new electrochemical materials. This can involve restoring or reformulating active materials, regenerating carbon-based components, or producing high-purity precursors that meet stringent performance requirements. The objective is to keep materials circulating within the same functional domain, preserving as much embedded value as possible. The second pathway is open-loop repurposing, where recovered materials are directed into other industries that can use them effectively without needing full battery-grade specifications. For example, carbon-rich fractions may be upgraded into conductive additives or functional carbons. Metal-bearing streams can be converted into catalysts, pigments, or specialty chemicals, and residual carbon or mixed materials can be engineered into electrode materials for supercapacitors or other energy-related devices. Together, these pathways create a flexible portfolio. Closed-loop routes maximize circularity, while open-loop routes expand market options and improve economics when direct re-entry into high-spec applications is constrained. A major barrier to material repurposing is feedstock variability. The incoming material stream is rarely uniform. End-of-life and production scrap sources differ in chemistry, formulation, and component design, and even small variations in additives, binders, coatings, and current collectors can change how materials behave during separation and upgrading. The condition of the feedstock also varies widely. Age, usage history, storage, and handling drive different degradation products and contamination levels that complicate processing. In practice, materials arrive in mixed forms, cells, modules, packs, or black mass, each with different impurity profiles and processing needs. This drives the need for stronger characterization, sorting, and process control. Without consistent inputs, it is difficult to deliver repeatable quality, which increases cost and slows scale-up. The main technical challenge is the mismatch between recovered materials and the tight specifications required for high-value applications. Recovered streams often vary in impurity levels and particle morphology and may contain residual organics from binders or electrolyte breakdown, which can degrade performance. This becomes critical when products have strict tolerances, because small differences in composition or structure can lead to major performance variability. Closing this gap typically requires upgrading through multi-step refining, such as washing, thermal treatment, leaching, precipitation, or resynthesis, which increases process complexity, energy use, and cost. There is also a trade-off. Aggressive processing can damage crystal structures or surface chemistry and reduce the value of the recovered material. While direct conversion and regeneration approaches are promising, they are still maturing, and scaling them requires robust process windows, strong analytical control, and proven long-term performance to compete with established virgin material supply chains. Safety is a primary constraint in material repurposing because incoming batteries and recovered materials can remain hazardous after use. Residual electrical or chemical energy can trigger short circuits, thermal runaway, fire, or explosion during transport, handling, and pre-processing, especially when batteries are damaged or their history and storage conditions are unknown. Repurposing also involves multi-step operations, discharge, disassembly, size reduction, and separation, and each step introduces hazards and variability. Mechanical processing can generate heat, sparks, and fine dust. Thermal or chemical steps can release flammable vapors and toxic byproducts, and electrolyte residues can be corrosive and difficult to neutralize consistently. Managing these risks requires specialized equipment, continuous monitoring, and strict procedures, which raises capital and operating costs and can limit throughput. Over time, progress depends on standardized handling, safer product design for disassembly, and better diagnostics to identify and route higher-risk feedstock before it enters processing lines. Economic and market dynamics often determine whether repurposing can scale beyond pilots. Repurposed materials must compete with established virgin material supply chains that offer predictable quality, mature infrastructure, and economies of scale. When commodity prices are low or virgin supply is abundant, repurposed outputs can lose cost competitiveness even if they deliver environmental benefits. A second constraint is demand uncertainty. Many end markets for recovered materials are fragmented and application-specific, and customers require validated performance, reliable volumes, and clear specifications, so qualification cycles are long and adoption can be slow. At the same time, variable feedstock and evolving product designs make it difficult to guarantee standardized supply. Finally, limited long-term offtake contracts and unstable margins restrict financing and increase perceived risk. Addressing these barriers typically requires tighter buyer-supplier alignment, clearer standards, and business models that recognize environmental value alongside production costs. Regulatory and standardization gaps are a major barrier to scaling repurposing because they create uncertainty for producers, buyers, and investors. In many regions, there are no harmonized requirements for repurposed material quality, such as impurity limits, consistency metrics, or performance validation protocols, so it is difficult to prove equivalence, compare suppliers, and build confidence in repeatable quality. Certification and traceability are also underdeveloped. Buyers often want verified provenance, processing history, and environmental claims, but consistent certification schemes and auditable tracking are not yet widely established. This limits access to regulated markets and reduces the ability to monetize sustainability value. In addition, liability and warranty responsibilities can be unclear, especially for high-performance or safety-critical applications, increasing legal risk and slowing contracting. Closing these gaps requires clearer definitions, interoperable standards, and coordinated policy frameworks so repurposed materials can be traded and used with the same confidence as conventional inputs. High-value upcycling is a major opportunity because it targets products with higher margins than basic commodity metal recovery. Instead of focusing only on bulk metals, upcycling converts recovered streams into functional, performance-driven materials, such as advanced carbons, engineered catalysts, adsorbents, and electrode materials for energy and environmental applications. This can strengthen the business case, particularly during commodity price volatility, by shifting value from fluctuating raw material prices to differentiated product performance. Upcycling also improves utilization of mixed or imperfect feedstocks where ultra-high purity is uneconomic, using tailored processing to achieve high performance in specific applications. Beyond the economics, it increases circularity by maximizing value retention and turning low-value waste streams into new products and supply chains that support more sustainable industrial inputs. Technology is widening what material repurposing can achieve by improving both control of incoming feedstock and the quality of final outputs. On the front end, advanced diagnostics and sensing, combined with data-driven classification, allow faster, more accurate identification of composition, contamination, and degradation, enabling smarter routing and tighter process control. On the processing side, direct and regenerative approaches aim to preserve or restore functional structures instead of fully breaking materials down, which can reduce energy and reagent use, shorten processing chains, and retain more embedded value. Advances in separation science, selective extraction, and surface engineering further improve the ability to tailor recovered streams into application-specific materials. Finally, modular and flexible plant designs help facilities adapt to changing chemistries and product designs, and when paired with digital monitoring and AI optimization, they can lower costs, increase yields, and accelerate scale-up, making repurposing more competitive and reliable. Material repurposing creates sustainability value by reducing dependence on virgin extraction and the environmental impacts of mining, refining, and long-distance supply chains. By keeping materials in productive use longer, it can lower life cycle energy use and emissions, reduce waste, and improve overall resource efficiency, especially for materials that are energy-intensive to produce from primary sources. From an environmental, social, and governance perspective, These outcomes support measurable progress on decarbonization and circularity targets, strengthen transparency and responsible management, and improve supply resilience by reducing exposure to upstream social and environmental risks. Repurposing can also align with investor expectations and enable access to green financing when impact reductions can be verified. Finally, it supports supply security by diversifying sources of critical materials and reducing dependence on concentrated or geopolitically sensitive regions, making environmental, social, and governance value a strategic driver for competitiveness, compliance, and long-term stability. Scaling material repurposing from pilots to a dependable industrial pathway requires coordinated action across design, infrastructure, and market alignment. Upstream, products need to be engineered with end of life in mind, designed for disassembly and designed for recycling. Standardized formats, clearer labeling, and reduced material complexity all improve collection, sorting, safety, and the quality of recovered streams. The next step is operational scale-up, moving from lab and pilot work to plants that deliver stable throughput, repeatable quality, and robust safety, supported by investments in automation, quality assurance, and process controls that can manage variable inputs. Finally, scale depends on stronger value chain collaboration. Recyclers and repurposers need clear requirements from material buyers, while original equipment manufacturers and designers need feedback on how design choices affect recoverability. Long-term offtake agreements, shared standards, and data transparency reduce uncertainty and unlock investment, making repurposing a reliable pillar of circular material supply rather than a niche option. In summary, material repurposing is becoming more important as battery use grows across mobility, electronics, industry, and energy systems. With rising volumes of end-of-life batteries, repurposing turns a waste challenge into an opportunity by keeping materials and components productive for longer and supporting a circular materials economy. Repurposing can follow closed-loop pathways, where recovered constituents are upgraded back into high-spec feedstocks, or open-loop pathways, where materials are converted into valuable industrial products such as functional carbons, catalysts, pigments, and adsorbents. This flexibility helps translate heterogeneous recovered streams into market-ready outputs. Scaling remains difficult due to variability in feedstock composition and condition, which complicates sorting and process control. Technical constraints, impurities, altered structures, and challenges in achieving consistent quality, combine with safety and processing risks to increase complexity and cost. Commercial and policy factors add further friction. Repurposed outputs must compete with low-cost alternatives. Demand is often fragmented, and limited long-term contracting reduces investor confidence. Regulatory and standardization gaps, around quality benchmarks, certification, and liability, also create uncertainty, making it harder to scale repurposing into a reliable, investable pathway. Thank you for your attention.